Welcome back to The Explainer. Today, we're going to completely demystify the physics behind something you've probably seen, well, a million times: how far a thrown object actually travels. Whether you're just tossing a baseball in the backyard or watching an Olympian launch a javelin, there are these fundamental, invisible rules governing that entire motion. And by the end of this explainer, you're going to know exactly how to decode them. Okay, let's dive into this. It's a wonderfully simple question, right? When you throw a ball, how do you calculate exactly where it's going to land? It feels like something that would require complex tracking machinery or just a lot of trial and error. But physics is actually the ultimate tool to solve this everyday mystery. All we really need is a tiny bit of information right at the moment of launch, and we can literally predict the future, at least the future of where that ball is going to hit the ground. Part 1, Anatomy of a Projectile. Let's break down its fundamental parts. First up, we need to clearly define what we're actually trying to measure today: the horizontal range. So this is the total horizontal displacement of a projectile from its initial launch point all the way to its landing point. In physics formulas, we represent this specific distance with a capital R. Notice that we aren't at all worried about how high the ball goes right now. We just want to know how far it travels across the ground from point A to point B. And this brilliantly illustrates how a single throw actually consists of two completely independent motions happening at the exact same time. When a ball leaves your hand with an initial velocity, which we call u, that velocity is split into two dimensions. On the left side, we have the horizontal velocity, which is what's moving the ball forward. We find this using the formula u times the cosine of theta, where theta is your launch angle. Then, on the right side, we have the vertical velocity, which is pushing the ball up into the air. That's calculated as u times the sine of theta. These two components, they don't interfere with one another at all. They just work together perfectly to create that classic arcing path. Now, here are two absolutely critical facts about how those components behave once the ball is actually in the air. First, look at that top point. Horizontal acceleration equals 0. Why? Well, because once that ball leaves your hand, there is absolutely no horizontal force pushing it forward anymore. It's just coasting horizontally. Second, we have the time of flight, represented by a lowercase t. This tells us exactly how long the ball stays airborne before hitting the ground. The formula for this is 2u sine theta, all divided by g, which, you guessed it, stands for gravity. Gravity is constantly pulling it down, which is what ultimately determines when the flight ends. Section 2, deriving the range formula. Let's find our master equation. Let's see how this builds step by step without getting bogged down in the weeds. Step 1, we start with our standard kinematic equation for distance. Step 2, we substitute in our specific horizontal variables, so r for range, our horizontal velocity, and our time of flight. Step 3 is where it gets really clean. Remember how horizontal acceleration is 0? Because of that entire right half of the equation, it just vanishes. It becomes 0. Finally, in step 4, we multiply the remaining parts together and use a super handy trigonometric identity, specifically that 2 sine theta cosine theta equals sine of 2 theta, to perfectly simplify our math. And that brings us to this beautifully elegant final formula. R equals u squared times the sine of 2 theta, all divided by g. This right here is the master key for projectile range. What is so absolutely fascinating about this is that it relies entirely on just 3 things: your initial velocity, your launch angle, and the constant downward pull of gravity. If you know those 3 variables, you know exactly where the ball is going to land. No guesswork required. Part 3, the formula in action. Let's look at a real-world scenario to prove this works. Imagine we're throwing a ball, and we manage to capture the exact conditions of the launch. Here are the precise variables from our source scenario. We have an incredibly strong initial velocity, our u, of 30 meters per second. The ball is released at a launch angle, or theta, of 50 degrees. And of course, since we're here on Earth, our gravity variable, g, is a constant 9.8 meters per second squared. So we've got our u, we've got our theta, and we've got our g. Now we literally just plug those values right into our master equation. The initial velocity of 30 gets squared. But definitely pay special attention to the angle here. Our actual launch angle was 50 degrees, but remember, our formula requires the sine of 2 theta, so we have to double that 50-degree angle to 100 degrees for the sine function. Finally, we divide that entire top part by our gravity, which is 9.8. And when we crunch those numbers, the result comes out to exactly 90.4 meters. Think about how powerful that is. Just by knowing the angle and the speed the ball left the hand, the math allows us to confidently predict it will travel almost an entire football field and land perfectly at 90.4 meters away. That is physics in action. Section 4, the secret to maximum range. Let's uncover the ultimate cheat code. Now, what's really interesting about this slide is that out of a full 90-degree quadrant, spanning all the way from a flat throw straight ahead to tossing it straight up into the sky, that highlighted 45-degree slice right in the exact middle is your magic number. A 45-degree angle mathematically guarantees you the maximum horizontal distance. So the crucial point is why 45 degrees actually works. And it all comes right back to how the formula was derived. Remember, the formula uses the sine of 2 theta. In trigonometry, the maximum possible value for a sine function is exactly 1, and that peak happens at exactly 90 degrees. So, if we want the sine part of our equation to be at its absolute maximum, 2 theta needs to equal 90 degrees. What angle do you double to get 90? Exactly 45 degrees. When you launch at 45 degrees, the sine function maxes out at 1, and your entire maximum range equation gracefully simplifies down to just your initial velocity squared divided by gravity. It's just a beautiful intersection of math and real-world physics. We've been exploring the flawless, perfectly friction-free environment of theoretical physics today, but it leaves us with a fascinating final thought to ponder. If 45 degrees yields maximum range on perfectly flat ground in a vacuum, how would real-world air resistance, or say launching from a high cliff where your landing point is way below your launch point, actually change the math of the perfect throw? Think about how those messy environmental variables might alter the clean physics we just explored the next time you're watching a long pass or throwing a ball yourself. Thanks so much for joining me for this explainer, and keep questioning the world around you.